Assalamualaikum and hi. And today my group and I is going to give a presentation about topic that is called as sound wave. So before we start, these are the name of our group members. And my name is Muhammad AFIQ ISYRAF HAKIM bin Muhammad NOOR. So let's get started. What are sound waves? Sound waves are composed of vibrating particles and allowing them to vibrate and collide with more particles. Sound refers to the physical sensation, longitudinal waves, that stimulates in the ear that happens when an object vibrates. When an object vibrates, it creates a pressure wave that produces sound. The pressure wave creates a vibrational motion in the particles. Sound waves causes the eardrum to vibrate, and the sound will be interpreted in the nerve impulses and then to the brain. Sound requires a driver. Sound is a mechanical wave, and mechanical waves require a medium to travel. Hence, sound cannot travel in the absence of matter. Because of this, there is no sound in space or in vacuum, because sound can only travel through a medium such as air, water, and solids. There are three categories of sound waves, which are infrasonic waves, audible waves, and ultrasonic waves. These waves are different, separated from each other based on their difference in frequency ranges. First, let's start with audible waves. Audible waves are longitudinal waves that lie between the range of sensitivity of the human ear, which is around 20 Hz to 20,000 Hz. These are the sounds that we hear every day, such as people talking and people shouting, and etc. Other than that, there are infrasonic waves, which are longitudinal waves with the frequency below the audible range. Frequency range for infrasonic range is below 20 Hz. As an example, whales communicate using infrasonic waves. So, what are the applications of infrasonic waves made by humans that are used in our daily life? Infrasonic waves are found to be useful to monitor earthquakes, charting rock, and petroleum formations below the Earth. Other than that, infrasonic waves are used in ballistocardiography and seismocardiography to study the mechanics of the heart. Other than that, there are ultrasonic waves. Ultrasonic waves are longitudinal waves with frequencies above the audible range. Frequency range for infrasonic waves is above 20,000 Hz. As an example, a dog whistle. A dog whistle helps humans to create a high frequency sound cannot be but can be heard by dogs. These whistles are used to train dogs. Other than that, there are ultrasonic waves. Ultrasonic waves are longitudinal waves with frequencies above the audible range. Frequency range for ultrasonic waves is above 20,000 Hz. As an example, a dog whistle helps humans to create a high frequency sound that cannot be heard by humans but can be heard by dogs. These whistles are used to train dogs.
Assalamualaikum warahmatullahi wabarakatuh. My name is MOHAMAD DANIAL bin AZMAN, and I'm going to continue about spherical sound wave. Spherical wave occur when a point source produce sound wave consistently in all directions, with the same sound wave energy radiate in all directions and the same speed of sound in all directions. On a spherical wavefront, the disturbance travels away from the sources. The wavelength indicates the distance between successive fronts. The oscillating sphere generates spherical sound waves that spread radially outward. In the most authentic situation, a wave that originates from the one source expands in a sequence of the spherical wave rather than moving in a straight path. Huygens principle we state that every point on a wave is a source of spherical wave. It is the fundamental of the mechanism for its propagation. The resulting Huygens wavelet design is shown in figures A and B for a two-dimensional plane wave and circular wave, respectively. Christian Huygens' insightful observation is that all the wavelengths in figures A and B, including those not shown but originating between those shown, form a new coherent wave that goes along the speed of sound to produce the next wave in the pattern. Furthermore, just as the wavelets in the forward direction form a new wavefront, they cancel or interfere destructively in a backward direction, allowing the wave to travel exclusively in forward direction. Speed of sound wave. Speed of sound wave is defined as the distance traveled by a point on a wave, such as a compression and a rarefaction, per unit of time. It is commonly given in meter per second. In scientific terms, this equals speed equal to distance over time. The greater the speed of a sound wave, the greater is the distance it will traverse in a same amount of time. If a sound wave is seen to travel 700 meters in 2 seconds, its speed is 350 meters per second. A slower wave will cover less distance in the same amount of time, possibly 660 meters in 2 seconds, and so have a speed of 330 meter per second. Faster waves cover more ground in a same amount of time. Now, in fluid, the speed of sound depends on the bulk modulus and density, and the equation is V equal to third bulk modulus over density of the liquid, while the speed of sound in a solid depends on Young modulus in the medium and the density. And in the equation, V equal to third Young modulus over density of the solid. Now, in ideal gas, the equation for the speed of sound is V equal to third gamma RT over M, where gamma is adiabatic index, R is gas constant, which is 8 or 8.31 joule per mole K. T is an absolute temperature in Kelvin, and M is a molecular mass. In general, the more rigid or the less compressible the medium, the faster speed of sound. This observation is analogous to the fact that the frequency of a simple harmonic motion is directly proportional to the stiffness of the oscillating object as measured by K, which is the spring constant. The greater the density of the medium, the slower speed of sound. This observation is analogous to the fact of the frequency of a simple harmonic motion in inversely proportional to m, the mass of the oscillating object. The speed of sound in air is low because of the air is easily compressible, because liquid and solid are relatively rigid and very difficult to compress. The speed of sound in such media is generally greater than the gases.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad ALIFF bin Muhammad ZAMRI. I will continue this presentation by explain about intensity for periodic sound wave. In previous chapter, it has been shown that a wave traveling on a taut string transport energy. So we would expect that sound wave also represent a transfer of energy. We are all very familiar with the loudness of sounds and aware that loudness is related how energetically the source is vibrating. The relevant physical quantity is sound intensity, a concept that is valid for all sounds whether or not they are in the audible range. Sound intensity is defined as the rate at which energy is transferred per unit area perpendicular to the direction of wave. It can be expressed by this equation, I equal to P over A, which is I stands for intensity, P for power, and A for area. Typical unit for expressing the intensity of a sound wave is watt per meter square. Based on the equation, we can say that the greater the rate at which energy is transported through it, the more intense that the sound wave is. Humans are equipped with very sensitive ears capable of detecting sound wave of extremely low intensity. Human ear can detect the sound's intensity between the range 1 times 10 to the power of negative 12 watt per meter square to 1 watt per meter square. High loss exposure is hazardous to hearing, which is why it is important for people working in industrial setting to wear ear protection. The intensity of predicted sound wave is proportional to the square of the displacement amplitude and to the square of angular frequency. The formula is I equal to 1 over 2 rho v times omega as maximum square. It also can be written in terms of the pressure amplitude. The formula is I equal to P maximum square over 2 rho v. Next is the intensity of sound in spherical wave. If a small spherical object oscillates so that its radius changes periodically with time, a spherical sound wave is produced. The energy in a spherical wave propagates equally in all directions. The intensity of the sound at a distance r from the source is I equal to power over 4 pi r squared, which is 4 pi r squared is the area of sphere. As a sound wave carries its energy through a two-dimensional or three-dimensional medium, the intensity of the sound wave decreases with increasing distance from the source. It is explained by the fact that the wave is spreading out over a circular two-dimension or spherical three-dimensional surface, and thus the energy of the sound wave is being distributed over a greater surface area. That's all for me. I will pass to FAUZAN to present for the next part. Thank you.
Assalamualaikum. Hi, I'm Muhammad FAUZAN FAKHRI bin Muhammad. So I'm going to continue on the presentation of the sound wave on the part of the Doppler effect. So without further ado, let's going on. So what is Doppler effect? Doppler effect is the change in the apparent frequency of sound depending on the relative motion of the sound source and observer. So when a source of sound and observer are in motion relative to each other, the frequency of sound heard by the observer is not the same as the source frequency. This phenomenon is called the Doppler effect. Doppler effect occurs for all types of waves. So figure below indicates on how somewhat the Doppler effect works. So let me show you how the Doppler effects works. So this illustration will help you understand further. So when the ambulance at rest, ambulance represent the source. Both observer on the sidewalk will hear the same frequency, whereas the boy and the girl will hear the same frequency emits from the ambulance, also the same sound. So when the ambulance is moving towards the boy, he will hear a higher frequency of siren and shorter wavelength of sound as he near to the source, while the girl hears a lower frequency sound and longer wavelength because the ambulance moved away from her. So the boy will hear the sirens louder, while the girl will hear less sound. Okay, so to help you understand further on how this mechanism works, I will provide you a video. So let's roll it. So after seeing that video, I hope you understand how the Doppler effect works. So the guy holding the phone recording the ambulance move towards him and against him. So when the ambulance move towards him, the frequency is increasing, whereas he hear more sound produced from the ambulance. So when the ambulance is leaving him, move away from him, the source is moving away from him, the sound produced is less. Okay, without further ado, let's continue. There are three cases of Doppler effect. So number one, observer in motion, source at rest. Number two, source in motion, observer at rest. And number three, observer and the source in motion. So the table on the right side I'll provide here is the symbol in the Doppler effect. So V0 is for speed of the observer, Vs speed of source, V speed of sound in air, Fs is frequency of source, F0 is the frequency of the observer, lambda s is the wavelength of source, and lambda naught is the wavelength of the observer. So let's continue. So number one, case number one, observer in motion, source at rest. So the observer moved with a speed of V0. A point is source is assumed remain stationary relative to the air. So the frequency heard by the observer will appear higher when the observer moves toward the source. So when the man moves toward the ambulance where the ambulance as the source is remain at rest, he will hear the frequency is increasing and the sound getting louder and louder because the observer moving towards the source. So this formula here is used in this case. So moving on to case number two, where source in motion, observer at rest. The source is moving in the direction of the observer at rest. As a result, the wavelength of observer is shorter than the wavelength of the source at rest. So when the source is moving towards the observer, the frequency is increasing. So when this ambulance moving towards the observer, the man, where the man is remain at rest, the frequency is also increasing because the source moving towards the observer and the sound heard by the observer will getting louder and louder as the ambulance near to him. So this equation, this formula is used in determination of the case 2. Okay. Okay, moving on to case 3. Observer and source in motion. So when both the source and the observer are in motion relative to Earth, the equation combined is to give the F0 equal Fs, V plus minus V0 over V minus plus Vs. So the upper sign, if the source and observer move toward each other. So when the man and the ambulance move toward each other, we will use V plus V0 over V minus Vs. So the lower sign apply when the observer and the source move against. So they move away from each other. So we will use V minus V0 over V plus Vs. Okay, understood? Good. So let's move on. So here we got application of Doppler, the application of Doppler effect. So number one, we got police radar gun. So the radar gun emits wave at a particular frequency, which when strikes the vehicle bounce back toward the gun. So the radar gun then measure the frequency of the returning wave, then eventually determine the speed. So figure below indicates on how the radar gun works. So the police shoots the radar gun towards the vehicle. So the sound wave produced from the radar gun move the outgoing wave and then reflected back to the radar gun, and on the radar gun it will display the speed of the moving vehicle. So it's very convenient, right, for the police to catch the criminal. Okay, we got second, we got the Doppler radar. The Doppler radar is usually for meteorologists utilize Doppler effect to determine the direction and velocity of raindrops, wind direction, and any other events. So this principle is very crucial as it allows meteorologists to predict weather pattern, including coming storm. So here, figure on the right figure here shows the Doppler radar. It shows the meteorologist will use the Doppler effect concept to determine on what weather is today. So it can be sunny, rainy, or predict disaster maybe. Okay, very also convenient. So let's moving on. Next, we got the application of sound. So what is the application of sound nowadays? So nowadays we got ultrasound scanner. So an ultrasound scan use high frequency sound wave to create image of the inside of the body. So it is suitable for use during pregnancy. So usually this thing used by the doctor for the pregnant woman. So here we got the image here shows that the doctor scan the belly of the woman to show the image of the fetus inside the baby, inside the woman, indicates on how months till labor day. Okay, also very convenient technology, goods. So next, secondly, ocean exploration. Ocean exploration is we using the sonar. So sound waves is applied in sonar device that is used to explore ocean. So usually the ships is equipped with the sonar, where they will use the sonar to determine on how depth the sea is. So here we got a figure here. It shows the sound waves is used as the sonar to determine on how depth the sea is. So they will also use the sonar to mapping the sea. They can also produce image like the baby before. Okay, next we got underground resource. So geologists use sound wave to search for resource such as oil, any other mineral under the earth. So same as the ocean exploration, geologists also use the sonar devices. Here we got the track. It emits the sound wave into the earth and reflected back and received by the geophone. So it will display on their displayer, whereas on where the mineral is, they will mapping or imaging the image on the under the ground. So geologists will read from the image where is located the oil or any other minerals. So good, very convenient technology. So we got communication, very common thing which used in the sound waves. So our vocal cord generates sound wave that are transmitted through the air to the ears of listeners. So when I'm talking here, my vocal cord generates sound wave that are transmitted to this microphone, and you will hear what I say. So next, we got hunting. So most animal use sound wave to hunt for food or detection of something. So here we got bats and dolphins. So bats sometimes using what called echolocation, whereas they use ultrasound wave to emit it and reflect it back to him, so they can imagine what is in front of him without see, only use sound. So in conclusion, sound is important in our daily life because it is used by human, animal, and any other things to perform various tasks. For instance, like before in communication, ocean exploration, underground resource, and hunting. And without, I hope that's all from me and my team. With that, we thank you.